Hi, introducing OpenStreetView-5M, the many roads to global visual geolocation. This project started as a hackathon with a few students of my lab. We wanted to code an AI that plays GeoGuessr, the game that drops you anywhere on Google Street View and you have to guess where you are based on what you see. We quickly realized that there is no open access dataset that would allow us to do that. What is available is Google Street View, which is expensive and cannot be distributed, or Flickr-based datasets with images who are typically not geolocalizable. Indeed, most pictures are either food, people, or pets, which do not contain a lot of geographical insights. To the other extreme, outdoor images are often tourist spots, which are biased towards certain regions and boils down to recognizing a few famous places such as the Eiffel Tower. So we created a new dataset with the help of Mapillary with over 5 million images across 225 countries. We also implemented a 1 kilometer buffer between train and test, so that a good geolocation score means that the model can locate an image based on geographical cues rather than just retrieving similar images from the training set. We then propose a simple framework for training geolocation models. We first embed an image using an image encoder, and then we use a simple geolocation head to convert the representation vector into coordinates. This allows us to benchmark several fine-tuning strategies. What do we freeze, what do we tune, and so on. We also measure the impact of various contrastive losses, and finally, auxiliary objectives, such as guessing the climate or the soil type at the locations. Here are some of our insights. Larger models, as expected, perform better, but the choice of pre-trained model has a huge influence, and a well-chosen VIT large outperforms a VIT big G, which has close to 2 billion parameters. In terms of fine-tuning, it is more beneficial to fine-tune the last transformer block rather than the entire network with LoRa. This suggests that the pre-trained patch embeddings are relevant, but the network must relearn how to combine them in order to predict a location instead of a class. Of course, fine-tuning everything leads to better results, but also more expensive. We can formulate geolocation as a regression problem by directly predicting the longitude and latitude coordinates. Or it can also be formulated as a classification problem by predicting the country, the region, or quaternary cell. We observe that models that predict first a cell and then regress the relative location within the cell perform best. You can find all these experiments, the dataset, on all of our code online. We also implemented a cool demo where you can compare your geolocation performance to two of our models, which is fun and also gives us more data for our human performance evaluation. Thank you.